Today, on how it's made. Binoculars. Sparklers. Rubber boots. And circular saw blades. A pair of binoculars is essentially a handheld double telescope. Light rays from the object you're viewing enter the lenses on the far end, the objectives. This projects an image just behind those lenses, inside the binocular's housing. The smaller eyepiece lenses you peer through then magnify that image. The objectives are curved, causing the image to appear upside down. To turn it right side up, each binocular half needs a glass prism. Using UV light-activated glue, workers mount several prisms on steel plates that take them through a series of grinding and polishing steps. Protective paint prevents any dust from contaminating the pristine surface. Grinding with diamond dust removes mere tenths of a millimeter of glass. Polishing with an even finer abrasive removes another 1/100th of a millimeter. At the end of it all, the three sides are perfectly flat. This minimizes reflection, critical for making the glass see-through. To make each prism, they glue two pieces of glass together at 90 degrees. This special machine ensures the angle is precise. A shot of UV light dries the glue. The first piece of glass rotates the inverted image 90 degrees. The second rotates it another 90 degrees, completing the flip. Now for the objectives. These curved lenses have undergone the same grinding and polishing steps as the prisms. Now they go through a 9-stage computer-guided cleaning process. After inspecting the lenses, a technician glues two together. A double lens limits a type of distortion that causes fringes of color to appear around the image. It's critical to match them to each other perfectly. If the alignment's off by more than just 1/100th of a millimeter, the image will be poor. This alignment machine displays a dot representing the center of each lens, so it's just a matter of matching the dots. A 2-second shot of UV light dries the glue. Next, a technician loads mineral pellets into a vacuum chamber. Their exact formulation is a company secret. The pellets produce an anti-reflection lens coating that lets more light come through the lenses. Inside the vacuum chamber, a beam of electrons evaporates the pellets into microscopic particles that coat the lenses. It's time to begin assembling the binoculars. First, the objectives go into the housing, which is usually made of plastic, aluminum, or carbon. Workers clean the lenses with a few blasts of compressed nitrogen. Then secure them in place with threaded holding rings. Now a few drops of glue behind the objectives, where the prisms will go. Another blast of nitrogen to remove any dust. Then they insert the prisms. This optical machine aligns the focal points of the prism and its corresponding objective. Then some more glue to lock in the positioning, and a blast of UV light to dry the glue. Now they silicone the objectives and prisms to the housing's middle section. Silicone creates an airtight and waterproof seal. This holding mechanism presses the parts together while workers drive in the screws. Onto the opposite end of the middle section go the oculars, the smaller lenses through which you look. Those also attach with threaded holding rings. Now, through a valve on each side, a machine sucks air from the housing and injects nitrogen gas. Nitrogen prevents the lenses from fogging up. A day after filling, they recheck the nitrogen pressure to make sure there's no leak. This factory puts all the binoculars it produces through rigorous testing, subjecting them to prolonged vibration, water pressure, extreme heat, freezing temperatures, and other trying conditions. After every test, inspectors make sure everything still works perfectly, both mechanically and optically. Sparklers have sizzled on the party scene for decades, adding pyrotechnical glitter to weddings and birthday celebrations. They evolved from more traditional fireworks and are the only kind that the consumer can handle when lit. Lighting one definitely means excitement is in the air. The splash of flash can last a minute or more, depending on the length of the sparkler. They start with steel wires that are about 48 centimeters long. They load bundles of them into the slots of a sorting machine. The machine vibrates, and the wires fall in single file into smaller openings. The operator then moves a spring-loaded wooden rack into position. It opens like the bellows of an accordion. The operator rocks the sorting machine overhead, and the wires drop into the slits of the rack, perfectly aligned. After 300 sparkler wires have fallen into position, the operator pulls a handle to close the rack. Now clamped in the accordion-style rack, the wires are ready to move on to the next station. Wires for parade sparklers are much longer, 91 centimeters in fact, which means they're heavier than ordinary sparklers. The operator loads each of these wires manually into a rack that's larger and sturdier than the last one. This system of loading is a lot more time-consuming, but parade sparklers are worth the extra trouble because they'll have a longer burn time, up to 4 minutes. Next, an operator loads boric acid and barium nitrate into a big mixing tank. The barium nitrate is an oxidizer and will help the sparkler burn. The boric acid is a neutralizer. He adds water and mixes in cornstarch. It will bind all the ingredients together. Next, he pours in some very fine iron filings. These bits of iron will give the sparklers their gold color. The operator then suits up in protective gear and closes the door. He's the only one allowed inside to load the sparkler's most volatile ingredient, aluminum powder. Once mixed into the wet slurry, the powder is virtually harmless, and they don't need to take as many safety precautions. Chain conveyors now move the rack of sparkler wires into position. An elevator lifts up the tank of the sparkler slurry to dip the wires in it. The next rack of wires then moves forward for dipping. 286 racks of wires move through this dipping station every hour and 45 minutes. They go through a second dipping station for one more coating. The two coatings double the diameter of the wires. After each dip, wires ride an overhead rail through an oven to bake the sparkler slurry until it's hard. An inspector then examines each sparkler. She checks for cracks and defects. Any wire that's flawed will be rejected because these sparklers have to outshine the competition. It takes her about 3 minutes to examine the 300 sparklers on a rack. They check the diameter of each sparkler by sliding it through a template, and they bend it to check its integrity. The sparklers have been stored for a week prior to packaging to allow them to cure. And now, they're ready for a party, and they're sure to be the center of attention. Wellington boots, billy boots, galoshes, by any name, rubber rain boots owe their existence to a 19th century American, Charles Goodyear. He invented the vulcanization process, a way to keep natural rubber from deteriorating. Nowadays, rain boots are made from a synthetic material called thermoplastic rubber, or TPR. They're functional, even fashionable. Making rubber boots begins with spools of polyester yarn for their lining. A colored spool adds a thin line of color to indicate the foot size of the lining. A computer-programmed machine crochets the yarn with 242 needles. As we can see in slow motion, each gate opens